Good morning, friends. So today we'll see the four, that is the flexibility approach. That is what the analysis of indeterminate structure by direct flexibility method. Okay. Flexibility method. So there are brother and sister called as the one is called as flexibility, another is called as the stiffness. So I'll write. Okay. So what is the flexibility? Okay, a displacement caused by the unit force. Displacement caused the unit force. See here, flexibility, displacement caused by unit force. When P equals to 1, it becomes delta. So that is called as a flexibility. What is the stiffness? Force required per unit displacement. Force required per unit displacement. How it is? Okay, so this is what we denote as delta, and here we will denote by K. So what is the flexibility? Displacement required per unit. Okay, we require displacement when there is a unit load applied on the structure or any material. So what is the displacement? It's called as a flexibility. Here, if we elongate a material of one unit, so what is the force required? That is called as a stiffness. Okay, so both are in the one family only, but they are in opposite nature. Okay, flexibility, displacement required per unit force, stiffness, force required per unit displacement. Okay. Now, simple. You understood what is the flexibility and stiffness? Now, already you know what is a indeterminate structure, where we cannot solve this structure or we cannot find the support reactions or by using equilibrium equations, that we call as a indeterminate structure. Correct? Indeterminate structure. So before going to the flexibility, okay. So we'll see one by one. So how to calculate the flexibility and stiffness. Okay. Now first we'll take the axial displacement. Axial displacement. So axial displacement, okay, that means force is applied axially along the member, okay, along this member, and the L is the length of a member, okay, A is the area of the cross section, okay, like this. So we know change in length equals to PL upon A, PL upon A. That is what this one is called as a displacement. So displacement when there is axial force, okay, change in length equals to PL upon A, PL upon A, correct? Now, so we'll put this in here. So delta divided by P equals to what? L divided by A. That gives us what? Flexibility. And P divided by delta gives us A by L. That is what the stiffness. So simple. Okay. So here, so when there is axial displacement, okay, axial displacement, so the axial flexibility equals to L upon A, and the axial stiffness A upon L. A upon L. Remember this one. Okay. Okay, students. This is about the axial displacement. Okay. Now, students, are you listening? Okay. This is very important concept. Okay. Remember this one. So the next we'll see transfer displacement. Transfer displacement. So transfer displacement is nothing but in terms of shear, correct? That is also, we can say, rotation without transfer displacement transfer displacement of one end of the prismatic member. With the with other end is hinged. That means what? Now this end is hinged, this end is rotating. Okay, because when there is a loading, this we have support, but it is not hinged, so it can rotate. So we'll have like this. Correct. So what is a rotation without transfer displacement? That means this end is rotating, that is A, we can call as B. So this end is rotating without displacement, displacement, without displacement. So what? So when we want to rotate this joint, we should apply a movement M. Okay. So what is the reaction here? What is the reaction here? And this rotation will be theta A. Theta A. So we'll find out when we apply a moment at a joint for a rotation. Okay, what are these reaction? So what is the reaction? Yes. So you know what is the conjugative beam method? Yes, students. Conjugate beam method. Have you studied this one? Students, you know what is the conjugate beam method? How to find out the displacement and deflection? So the rotation means theta and the displacement is delta. Okay. So when we apply a moment, we'll have this rotation. When we apply a force, we have displacement. Now I'm asking you, you know what is the conjugate beam method to find out the displacement and deflection? Yes, students, I'm asking you. Hello. You know conjugate beam method or not? Are you listening, students? Okay, if you know, see, this method is to find out the displacement and deflection, correct? So that is also called as M by EI diagram in this method. That means, suppose there is a cantilever, okay, and there is a load W. If you want to find out the displacement and deflection at the end, so what is the bending moment? Bending moment will be WL, correct? So that WL is loading, then we'll calculate the reactions, correct? So what is the reaction here? Yes, this reaction RB and RA. So what is the RB reaction? RB into L equals to WL by EI into half into L. This is total load. Total load will act as a CG point. So one third of L. One third of L. So LL get cancelled. So what is the RE equals to WL square upon 6 EI. W upon 6 EI. And RA will be, you take RA equals to WL upon EI half into L into 2/3 of L, correct? So here into L get cancelled. It is WL square upon 3 EI. So this reaction gives us a slope. So the slope at this end, that is theta, equals to RB, that is WL square upon 6 EI. Okay, so like this we can use this conjugate bend method to find out the displacement and rotation. Now the same here. Now our case is we have roller support, and here we have pin support, and we have applied the moment at the end. So first you draw the bending moment diagram. So M, this will be diagram, correct? So M is a moment at this end and 0 at this end, okay, divided by EI. You calculate the reactions, calculate the reaction at the end. So that is also, we can call it RB dash and RA dash, correct? So what is the RA dash? RB dash equals to what? Half of M by EI into L, correct? Into L, and it is L by 3 into L. L get cancelled. So what we have? ML upon 6 EI. ML upon 6 EI, and RA ML upon 3 EI. 3 EI. That means the theta at A. So this reaction gives us, I told, this reaction gives us a displacement. So the displacement at A, theta A equals to reaction at A 3E gives us ML by 3EI. ML by I. So what is M equals to 3EI, 3EI theta A divided by L. Theta A divided by L. Theta A divided by L. Okay. Now the reaction will be, so the reaction will be what? So from that relation, we can find out the stiffness and flexibility. That is what M upon theta A gives us what? 3 EI by L. So here force required per unit displacement. force required per unit displacement. So here what? A moment required per unit rotation. Per unit rotation gives us flexibility. Correct? And theta A upon m equals to L upon 3 EI, that gives us a stiffness. That is a displacement rotation required per unit. When you apply the per unit moment, okay, unit moment. So what is the displacement? That is rotation, L upon 3E. Okay. So here remember, whenever there is one end is rotating or any force is applied, what is the flexibility and stiffness? Remember here, on other end should be pinned or hinged. Okay. So that time we have this one. Okay. Okay, students. So remember this one. So A and B. So the displacement at A equals to how much we got? ml upon 3EI. So the flexibility equals to L upon 3EI, and the stiffness equals to 3EI divided by L divided by L. So we got M equals to, and these reactions, M equals to what? 3EI divided by L into theta A. So this reaction gives us 3EI theta A divided by L square, and this one 3EI theta A divided by L square. Remember this one. So when there is a moment of this force, if we applied, we'll have these reactions. Okay, this is very useful. Okay, so because we have coordinate 1, 2. Okay, so where we applied the unit rotation? At here. That means if you have matrix delta 1 1, delta 1 1, that means, sorry, flexibility delta 1 1, that means at point 1, when we have what is the rotation, that is what 3EI by L into theta I, delta 1 2. What is the meaning? So what is this rotation? What is the rotation at node 1 due to the moment applied at 2? Now the moment applied at 2 is what? 0. Correct? Moment applied at 2 is 0. Correct? Like this. Okay. Now this is about the rotation. Okay. So like this. So we have matrix delta 1 1, delta 1 2, delta 2 1, delta 2 2. Like this. So here what we have only 3EI by L into theta A 0 0 0, because there is no rotation at this end. Okay, so like this. So that is what the last unit. Okay, so remember this one. So you should remember this sketch. Here what we have? Rotation without transfer displacement. Rotation without transfer displacement. Okay, remember. Okay, now we'll move to the next. Same rotation without transverse displacement of one end of a prismatic member with the other end is fixed. Now what we have this condition. What is the rotation at this end if other end is fixed? Other end is fixed. So I'm not showing calculation. You can find out directly like this. So you should have like this. This is RA1, RB1. The moment will be here the same. Okay, so loading diagram will be like this. M plus RAL. Okay, so this will be EA. Here will be EA. Okay, you find out. So directly I will write. So we have RA dash equals to ML upon 4EI if we do the calculation. RA ML upon EA. So this is what reaction gives us a slope at this end. So this is nothing but theta A equals to ML upon 4EA. So from that we can here okay students. So and stiffness M upon theta A equals to 4 EI by L equals to K. That is what the stiffness. That is what the stiffness. Okay. So remember, whenever there is a rotation at one end and further end is fixed, flexibility gives us L upon 4 EI and stiffness gives us 4 EI by L. Okay. Now we'll see the reactions. So we have reaction here, moment here, correct? All these things. So this gives us 6 EI divided by L square into theta A, 6 EI divided by L square into theta A, and the moment, so this is what M equals to 4 EI by L into theta A. Carryover moment will be half, same direction, This gives us 2 EI divided by L into theta A. Remember this one. So this diagram you remember. So what is the changes will happen? Okay, when we apply the moment at this end, the reaction will be like this, and the moment at further end will be like this. Okay, remember this diagram. Remember this diagram. Okay. Okay, students. Now next. Now the rotation is over. We have seen the two terms of rotation. Further end is pinned and fixed. Now we will see the transfer displacement. Transfer displacement without rotation of one end of a prismatic member with the other end is hinged. Other end is hinged. So what will be the here? See here. This is hinged. So now this one we have a transfer displacement like this. Okay. That means earlier we have A here, here B, but due to the transfer displacement, this end goes to here, and we have a displacement in vertical direction we call as delta. We call as a delta. We call as a delta, and here we have the length and EI of a member. Okay, that means earlier beam is like this. So I'm not here. It is pin support. Okay, now this beam is goes to here. So what is the movement? Is the reaction here? What is the reaction? So we have to find out. We have to find out. Okay. Now, so there is a displacement. Correct. Now we have applied which force? RA. Here is a displacement. So we required force to have the displacement. We require force to have the displacement. So I have applied the force. Okay, I applied the force. Correct. So that gives us this displacement. So this force, here again we have moment. This moment created. So this moment is equal to 3 EI delta. 3 EI delta upon L. You can say L square. And this reaction will be rotation. So M by L 3 EI delta upon L cube 3 EI delta upon L cube. L cube. Okay. So remember this diagram. So this is what the displacement. That means what? Here we have applied the P force, suppose, correct? P force gives us displacement is 3 EI delta upon L cube. So delta divided by P equals to what? L cube upon 3 EI is a flexibility, and P divided by delta gives us 3 EI by L cube stiffness. So remember this one. So whenever there is a like this, okay, so we have position like this. Okay. Okay, students. Now we will see the further end is fixed. If there is a further end is fixed, what is transfer displacement of one end for prismatic member if other end is fixed with the other end is fixed. So here if you apply a P force, correct, so this joint get displaced here, and we have movement here, correct, the same movement will be here, and we have the reaction that I will draw here. Okay, this gives us 6 EI upon L square into delta, same 6 EI delta upon L square, and this reaction will be like this. If this is anticlockwise, sorry, the moment are anticlockwise, so the moment this reaction produce the moment clockwise, so this one will be upper side, this will be downward side. Okay, so 12 EI upon L cube into delta, 12 EI L cube upon delta, L cube upon delta. So what is the force? This is the force reaction. That is P gives us 12 EI upon L cube, delta is a displacement. So P divided by delta equals to 12 EI by L cube. Force required per unit displacement gives us stiffness. And displacement upon P gives us L cube upon 12 EI gives us flexibility. Remember this diagram. Remember this diagram. Okay. Okay, students. Now we have seen all the cases: axial forces, axial displacement, transfer displacement, all these things. Correct? No. So we'll draw one table, so it will be very useful to remember you. So if you remember this table, so it will be okay. So here's serial number, type of displacement, and here I have flexibility, delta, and here I have stiffness, K. So serially one axial displacement. When there is axial displacement, what? So we have axial displacement dl when we have P4. So what is the flexibility? Simple, dl equals to PL upon AE. This is nothing but L. Del divided by P is what? L upon AE. Flexibility L upon AE. And stiffness is just opposite, AE upon L. Correct? Now the second one. Second one is what? Transverse. Here we have seen the two conditions. Far end fixed. If far end is fixed, okay, so just now we have seen when far end is fixed, okay, what is the transfer displacement? That is flexibility. Far end is fixed, what is transfer? Flexibility is L cube upon 12 EI. L cube upon 12 EI. It will be 12 EI upon L cube. Simple. Second one, far end hinged or pinned. If it is hinged, what we have displacement? Flexibility L cube upon 3 EI. L cube 3 EI. And here 3 EI divided by L cube. Correct? Now third one, bending. Bending is nothing but the moment or flexure. When there is a moment applied, what is the rotation? When there is a moment applied, what is the rotation? Okay. So first, far end fixed. Far end is fixed. What is L upon 4 EI? And 4 EI by L. B, far end pinned or hinged. L upon 3 EI. Here 3 EI upon L. If you remember this one, it's okay. Okay, if you remember this one, it is enough. Okay, for the flexibility, stiffness method, flexibility method, and matrix method. Okay, so now we'll see the nodes. What are the nodes? What is the system of nodes? This is very important. Okay, listen to me. When a point, or we can say this is a member, point is free, and is free. Is free. This can be displaced vertically. Okay, displacement vertically, horizontally, and it can rotate theta, delta V, delta H. That means each node have three displacement. That is 2R called as a transport displacement. That is one we called as axial displacement, one we called as a transverse displacement, and one is called as a rotation. So this provides axial force. Transport displacement provides the vertical force, and the rotation provides the moment. When there is a moment applied, we'll have the rotation. So each end we have three displacement. Each end we have three displacement. Now, so I'll give each displacement as a node number. Each displacement as a node number. Each displacement as a node number. So I'll give the axial direction 1, vertical direction 2, rotation 3, here also same, 4, 5, 6. Correct? Now, so what is the delta 1, 1? So this is what the flexibility. Delta 1, 1, remember. So what is the displacement? Now, 1 is a horizontal axial displacement. What is the axial displacement? So this is what? Displacement required per unit force. Correct? So what is the displacement along 1 when we have unit force, unit axial force? Unit axial force. What that one? So already we have L upon A. L upon A. Now the arrow is showing along this one, that's why positive. Now what is the delta 1, 2? Delta 1, 2. So what is the displacement along this axial direction when we apply the force along 2? Along 2, 0. There is no effect when we apply vertical force. Okay, unit force. We have the reaction. We have only the moments and reactions. Delta 1, 3. What is the displacement when we apply the moment? No, 0. Because rotation, only rotation we have the reactions. Correct? Now, delta 1, 4. Yes. So we have L upon A. L upon A. Now force is in this direction, so we have, I call it minus L upon A. Minus L upon A. Okay. So remember now 1, 5, 1, 5. So 1, 5. What is the vertical force is applied in this displacement is 0, and 1, 6 also 0. Okay. Now delta 2, 1. So what is the displacement along the vertical direction when we apply the axial unit force, unit axial force? There is no effect, so 0. Delta 2, 2. Now it comes. So when we apply the unit force, okay, unit force along this direction, this member get displaced by amount of delta. So we have the reaction, correct? So what is that one? Now the far end is fixed, we can say, because we have 3 displacement. So what we have? L cube upon 12 EI. delta 2 3 delta 2 3. Now, so when we apply the moment at this position, okay, that is rotation, so we have this reaction in the opposite direction, correct? So that gives us what? Rotation, far end is free, L upon 4A. Downward direction, that's why negative. That's why negative. Okay. So like this, we have to arrange this one along these nodes. Okay, we'll have extra lecture at 3 o'clock. Okay, that time I will explain. Okay, till now you can take a break. Okay, so we'll meet at 3 o'clock. Okay, students, till now you can have the break. For that one, you can use this book. Is what the structure analysis by matrix approach method, Pandit and Gupta. Okay, so here we have this flexibility and matrix matrix 4-1. Okay, okay, so we'll stop here.